It's getting towards the end of this award, so I'll be talking a bit about the results we're getting, which is kind of exciting. But before I get started, I've got to recognize that this work is due to a cast of thousands. All right? This wouldn't happen without the collaborations between both professors and students and postdocs in what we call the M-Body shop at the University of Washington Astronomy Department, and with people at University of Illinois in Sanjay Kelle's parallel programming lab. We couldn't do the scaling to blue waters without the help from his group. So what I will be talking about, I've outlined here, trying to address some of the topics that were given to me, starting with scientific background, how we're doing on blue waters, why we need blue waters, talk a little bit about the scaling, and the exciting part, the results, and paid program, and then else, and then actually some broader impacts. So why it matters, what are we trying to study? Our picture of the large-scale structure of the universe is actually very good. We have this model that we call the cold dark matter model. It predicts a certain spectrum of fluctuations on the largest scales. This is an actual observation of those fluctuations in the cosmic microwave background. It's a map of the temperature of the universe just 130,000 years after the Big Bang. And the spectrum you get from here matches very well the power spectrum that you predict from the cold dark matter model. What doesn't work so well is how do you turn these kinds of fluctuations into things that look like this. This is a galaxy much like our own Milky Way, and predicting the exact structure of the Milky Way is a more difficult challenge. Part of the challenge is that the structure you see here is mainly dominated by gravity, which in turn we found out is mainly dominated by the stuff we call cold dark matter. We don't know what it exactly is, but we have good ideas what its properties are, and hence we get good predictions on large scales. The structure you see here is not so much the dark matter, although it influences the structure. What you see here are baryonic processes. And although baryons only compose 5% of the mass energy density of the universe, baryons are very important. I mean, some of my best friends are baryons. But they're complicated. Some of my friends are complicated. And so there's this processing through nucleosynthesis inside stars. There's radiation from the stars. That's those pink regions you see there. Very difficult physics to understand, but that's all physics that's making this picture. And so if we really are going to model the formation of a galaxy, we need to understand the formation of stars, and that's particularly difficult. Brian did a wonderful job of explaining some of the difficulties, so I'm just going to outline why it's so difficult, and because there's a lot of complicated physics going on. The gravitational instabilities, that's difficult in itself, but that's kind of the easy part. Once things start to collapse, magnetic fields become important, radiative transfer becomes important, the chemistry within molecular clouds and within a radiation field becomes important. There's turbulence that's driven on large scales by the differential rotation of the galaxy. And there's also turbulence being driven by the supernova explosions. Those stars at the end of their lives send shock waves into the material, which you also have to model. And these are all happening on scales that are difficult, if not currently impossible, to resolve when you have cosmological simulations. And just to put a picture on how complicated it is, this is a molecular CO carbon monoxide map of the Taurus cloud. And the colors are various velocity channels, a couple kilometers per second per channel. But the key thing is to look at is the scale bar there. This is detailed structure that's happening on 4 parsec scales. This picture is on 30 plus kiloparsec scales. And of course, this is embedded in a 100 kiloparsec dark matter halo, and of course, evolving from the even larger scale structure of the universe. So we have this resolution problem. If we're going to do that simulation of a galaxy, we do need cosmological scales, tens, if not more, megaparsecs. But we need the sub-kiloparsec scale because that's the size, the scale height of the disks that we saw. But the star formation, at least currently, we can't get down to parsec scales. Brian's getting there. Good job. But so we need a subgrid model that captures the things we do understand. We know that stars form in high-density environments. We know that there is feedback from supernovae and stellar winds that limits the amount of gas that turns into stars. We know we have these resolution issues. When we take 10 to the 4 degree gas, it doesn't cool very well. We take 10 to the 6 degree gas, it doesn't cool very well. You mix them and you get 10 to the 5 degree gas, and that cools like gangbusters. And so we got to mitigate that. But we can do that, and we can model current day galaxies with reasonable subgrid models. So the challenge we have for blue waters is to do I will call it nearly cosmological volume with the kind of resolution that we've had to model individual galaxies. And the requirements are that you need millions of resolution elements per galaxy. We use n-body SPH, so our resolution element we call a particle. And we want to model a population of galaxies. And I chose this volume because it matches very well some of the deep surveys from the Hubble Space Telescope. The other thing that's very difficult is that we want to take those deep images of galaxies and relate them to galaxies today, which means that we've got to integrate this volume for the age of the universe. So how do we tackle this problem? Let me talk a little bit about the software development. Scaling to large processor count, we decided that we need to go beyond MPI and let other people think about the messaging and the load balancing. And we collaborated with the ChaNGa group, which is the C++ based language where you over-decompose your problem, and the runtime system moves the pieces of your problem around the system in order to balance load and minimize communication. The application that we developed, we call ChaNGa for Charm N-Body Gravity Solver, and as well as being this massively parallel smooth particle hydrodynamics code, we've included a lot of the subgrid physics. SMBH, sorry for the acronym, that's supermassive black holes, which I'll explain a little bit, but it's necessary to reasonably model these galaxies to the current day. And we've done very well at scaling. If we take a uniform distribution of particles and throw it onto blue waters, in this case, notice that basically due to the load balancing and of the ChaNGa++ system, we were able to scale to 500,000 cores, where I count the integer units as cores here, just to be clear, with better than 90% parallel efficiency. I'm kind of cheating here. This is a uniform volume. Let me show you what the universe really looks like. It's not so uniform. So this is, again, this is a 25 megaparsec volume. You're looking at a couple billion particles here. 100 million or so particles are in that large group in the upper left. And so you get an idea of the gross imbalance of the work that has to be done. And this is where CHARM++ comes into its own. It has the ability to move things around to tackle these imbalances and optimize the communication, although we have, there are issues because we have fixed costs for each small time step. So efficiently doing domain decomposition and tree building is a scaling challenge. Nevertheless, here's a picture of a similar volume, but the color scale here, first of all, particles are actually processors, and the colors are the load associated with each processor. And actually, these are virtual processors. And so what CHARM++ is able to do is to take those virtual processors and map them onto the Blue Waters nodes. And so now we have the particles colored by the node they live on. And you can see how it's managed to divide up. And notice it divided that big cluster up into two pieces, and it's also moved that one boundary up because it knows it has a lot more load on the top half of the volume than the bottom half. And so even with this kind of clustering, we can get scaling up to 128K cores on Blue Waters. Efficiency not as good as before, but understandable, getting 80% efficiency for 2 billion clustered particles. So this was actually beyond my imagination when I started this project, so I'm really happy at how well this has gone. So the actual simulation we did is this 2 billion particle simulation, forces below a kiloparsec, getting down to 100 parsecs, and below 100 parsecs in the gas resolution. And what do we get for a galaxy population? So here are some results that Lauren Anderson, it may be being submitted as I speak, is comparing the luminosity function of galaxies. So the vertical axis is number density of galaxies as a function of their, sorry, astronomy language, UV magnitude. So magnitudes is this logarithmic scale, which more negative is brighter. So bright is towards me. And we're looking at various redshifts, 4, 5, 6, 7, 8, 10. So that's looking further back in time. The colored is from our simulation. Those gray bands, you can see most clearly at the bottom, are from Hubble Space Telescope data from last year. And so you can't see the gray bands that well on the top panels because it matches so well with our simulations. A little more discrepancy going back in time. But the other thing is, of course, the gray bands cut off at about -18 because you can only observe so faint. And so we have a prediction here that beyond the faintness that galaxies that we can currently see with the Hubble, we have this large population of faint galaxies. And note there's an alpha on each of these plots, which is the faint end slope. And if alpha equals 2, -2, or more negative, that means you have more stars in low-mass galaxies. So our prediction is that the low-mass galaxies are dominating the luminosity of the universe at this epoch, which also means that they might dominate the amount of UV light that is going out into the intergalactic medium and reionizing it. So we did the calculation, or I should say, Lauren did the calculation. Again, part of this paper that's being submitted. The black points are from our simulation showing the amount of UV flux of UV photons. The green dashed line is the number of photons you need to keep the universe ionized. And notice that they cross over at about redshift 6 or a little greater, where we know that the universe has been reionized. So the blue are observations of the ionizing flux, and then the red is sort of a single quasar at high redshift that tells us that the universe has been ionized back to that particular quasar. So you can integrate the ionizing flux over those redshifts, and we can get the fraction of H2, that's ionized hydrogen, as a function of redshift. The yellow is from our simulations, again showing that we can reionize the universe by a redshift of 6. And then on the other side is cosmic microwave background observations. We can tell from polarization measurements what essentially how many neutral atoms are between us and the cosmic microwave background. And so the green curve is our prediction for that, and the hashed dark region is the Planck results, Planck/WMAP results for what we call the optical depth to the ionizing background. So remarkably, these faint galaxies can reproduce our observations of the reionization of the universe. How much time? Let me go quickly here. Another thing we got out, lots of results to talk about, is that, of course, that -2 can't go forever. And so the plots I showed before, we cut off at around -14. Now, different plot. This is the mass in stars on the vertical axis against the halo mass. The colors show you the brightness of the galaxies. So the dark blue are the galaxies I was talking about before. As we go fainter, we see this large scatter in galaxy luminosities, even if you're living in the same halo mass. And we also see a very steep shutdown in the luminosity of the galaxy. So there is ultimately a shutdown. And again, this is work by Farah Munshi. I'm hoping this paper will be submitted shortly. I mentioned to get to the present, we also have to include the effect of supermassive black holes. Yeah.
I'm sorry, on that last figure, what redshift is that?
Oh, sorry. This is redshift 0. So this volume, Farah has been working with a smaller, what we call zoom-in patch to get these results. Notice that the resolution here is much higher than what I had in those previous results. Supermassive black holes. We have found that, particularly in the centers of large galaxies, supernovae are just not energetic enough to shut down star formation. We need something more energetic, and we know that there's these big things sitting even in our own Milky Way that can provide that. We call them active galactic nuclei. We believe they're powered by black holes. And so we have this three-piece methodology for modeling those black holes. Let me just go to the movie. So we model the black hole seeding. So the blue is the gas. You'll see some white points pop up. Those are supermassive black holes, million solar mass black holes. Those black holes will, after they form, they will merge as the galaxies merge. And also as they merge, gas gets driven to the center. As it goes down the black hole, they're very messy eaters. And so a lot of radiation gets fed back, and you'll see the red coloring shows you the hot gas being spewed out by the active galactic nuclei. And then on top of that is a stellar population colored from blue to red as the stars age. I'm short on time, so we'll have to cut short the enjoyment of the movie and talk about, again, this relationship between stellar mass and halo mass. 10 to 12 is roughly a Milky Way mass, and that's where supernovas start to break down. With the addition of the supermassive black holes, we can match that gray patch, which are the observations, with our simulation, which is taken from our 25 megaparsec volume with black holes. We call it Romulus, at a redshift of 0.25. So roughly 3/4 of the age of the universe, nearly to the present. We can look at the luminosity function of those active galactic nuclei that we produce and compare it with observations. Running out of time, let's just say they match. Another relationship we know about is a relationship of the black hole mass with the stellar mass of the galaxy it lives in. The gray line is again the observed relation, and our points are from our blue water simulation. So notice that we match very well at the high end. At the low end, there is a well-known scatter in that relation that we also reproduce. Let me take it. So great results. Let me talk about the paid program. We've got a little support for our GPU implementation. And we wanted to do a couple things to it. It was written for an ancient GPU. We wanted to update it. We need to handle SMP GPU programming and the usual CHARM++ load balancing. A number of personnel has helped us with this. Simon, Michael, I know is here. Simon and Michael are there. And Pengwing and Tom Gibbs from NVIDIA helped us out. So GPUs are fast. Just note that, say, compare the red line, which is sort of gravity time in seconds as a function of the number of nodes, that's running on an XK GPU, compared with the green line running on that same XK node just using the CPU cores. We wanted to improve on this, so this is what it was before we started improving on it. What happened was we got the Pengwing. It's nice to have an NVIDIA guy look at your code, and he knows the details of the GPU. So he was able to eke out a 2 times performance out of our main kernel because he knew about these details of the machine. And combined with another kernel speed up, we got an overall speed up of 60% in the throughput of our code. SMP and GPU, right? So we got distributed computing, we've got OpenMP and threading, and now we have to do all that plus feed stuff to the GPU. This is tough. In particular, worrying about memory management, both on the host and on the GPU. This is still work in progress. Let's just say it's a challenge, but we hope to we're making headway. Let me finish up by talking a little bit about broader impacts. And the great thing is that the simulations are becoming high enough fidelity that you can essentially observe them. And this makes them very attractive to, say, set an undergraduate at analyzing the simulation. So at the University of Washington, we have this pre-major in astronomy program. We tool up these freshmen with observing tools. We get them working together, and this gives them incentive to stay in STEM education, where a lot of people, they get to college and they see all the math courses they're going to take, and they say, business school looks pretty good. And so showing them the light at the end of the tunnel, the exciting research that they can do if they just stick it through is key. And particularly with simulated data, right? The images are spectacular. It's cosmology. I mean, they're really excited to look at this stuff. And they've got these tools because it's analyzing simulations is so similar to analyzing astronomical images. And so we have, a couple of first-year students. We give them the data, and they're able to make, this is what we call a Colormagnitude diagram of galaxies in our simulation. Those of your astronomers know about the blue cloud, small star-forming galaxies in the lower part of the diagram. And then there's the red sequence elliptical galaxies that are, we call them red and dead on the top, and these freshmen were able to analyze the data and pick out these galaxies, look at their morphologies, look at their star formation histories, look at the effects of supermassive black holes, and get really excited and get some interesting results. Okay, Greg is standing up, so let me just leave you with some 3 takeaways. Scaling is difficult, it's still going to be difficult, and I really needed to work with computer scientists to get this done. That reionization stuff, I didn't expect to be doing that, all right? So sometimes your breakthrough is not what is actually written in your proposal. And finally, this is exciting stuff to present to upcoming scientists. All right, so I'll thank the people that funded me.